Okay, so I think we can start. It's 10:02. So hi, my name is Elisabeth Christ. I volunteered to be the session chair. That's the first time I've ever done that, so bear with me. This is my presentation on PFAS destruction in high-strength waste streams. We're going to be going over actually a couple case studies on low-energy electrochemical oxidation. So I'm going to be talking about PFAS and why low-energy electrochemical oxidation is... Yeah, definitely. Why it's important for the PFAS remediation market. So PFAS, I'll just start from the beginning. PFAS is a man-made substance that is manufactured to be extremely temperature and pressure resistant. It's used in a variety of household objects for waterproofing, oil proofing, as well as firefighting foams for fuel-based fires. They are so long-lasting and seemingly undestroyable because of the carbon-fluorine bond, which is the strongest organic bond found in nature, and this contributes to their ability to bioaccumulate in the environment and in our bodies. And when it gets in our bodies don't really know what to do with them, so they just get seated in the organs that are usually meant to filter out toxicities that we ingest. So that's namely the liver and the kidneys. And because of these linkages to human health effects, PFAS has made it into the public eye, and there has been a lot of pressure on the EPA to regulate these compounds in drinking water, wastewater, and industrial waste. There are currently no federal regulations yet. However, according to the EPA's PFAS strategic roadmap, they should be coming out with a ruling in the next year or two. And some local and state governments have taken it upon themselves to put in regulations of their own, starting to regulate PFAS discharges in drinking water, wastewater, and industrial wastes, such as landfill leachates. And the most recent infrastructure bill did set aside $10 billion for PFAS monitoring and remediation. But what exactly does remediation look like? What solutions are available for treating PFAS-laden waste streams? And I come from the wastewater treatment space, and the options for PFAS treatment are quite limited. There are a few sequestration technologies that do a great job at filtering out PFAS from water. This allows drinking water plants to safely discharge to piping systems and allows wastewater treatment plants to safely discharge to the environment, but you're still left with essentially this filter media or this very concentrated liquid side stream that's now saturated with PFAS, and currently our solution is to take that PFAS and essentially send it somewhere else. I've heard of them just sending it directly to a landfill. I've heard of people mixing PFAS waste with a cement amendment and putting that into a landfill, so at least it's not mobile. I've heard of people sending spent granular activated carbon that's reached its PFAS breakthrough point to Canada. And I've heard of certain EU countries sending their PFAS waste back to the United States, actually back to, I believe it's the Chemours plant in North Carolina, which when the local community found out about that, they were not very thrilled. And then what do you think that Chemours is going to do with it once it gets here? They could put it into a landfill here, they can incinerate it here, or they can deep well inject it here. And that's about it for the list of disposal options for PFAS. And there is the threat that these places will no longer be accepting the PFAS waste because they don't want to take on the liability if PFAS becomes federally regulated. And then just quickly, some hesitation on incineration is that it might not be completely destroying the PFAS, so there's risk of air emissions. And to date, it's been very hard to measure PFAS in air. In water, it's slightly easier. And then with deep well injection, there is the threat of aquifer contamination, but we can argue about the validity of those claims. No matter, that's still only 3 tools in your toolbox for PFAS remediation. So that is essentially why the market is looking for a PFAS destruction solution. So a little bit about PFAS chemistry. PFAS are characterized by a hydrophobic carbon-fluorine chained tail and a hydrophilic functional group as its head. 2 main types of functional groups are the sulfonic acids and the carboxylic acids, and there are many variations of these functional groups and many different chain lengths, so this attributes to tens of thousands of different PFAS species. And you can also have precursor species, which when oxidized turn into PFAS, and those are what are commonly found in firefighting foams. So, depending on if it is a sulfonic acid or a carboxylic acid, you can classify these compounds into long chain and short chain, with long chains being 6 to 8 carbons, and short chains being 5 to 7 or fewer carbons. And then not shown here on this table are ultra short chains, which contain 3 or fewer carbons. And it's just important that I mention the chain length because in some regulation, sometimes chain length will be referred to, and also the removal efficiency of certain sequestration and destruction technologies can vary based on the chain length. So there are a handful of different destruction technologies listed here. Some are not yet commercially viable. Electrochemical oxidation is the farthest along in terms of commercialization, and that's because it's one of the few technologies here that operates at ambient temperatures and pressures and requires almost no chemical addition. So no matter how these systems operate, they're always either an oxidation or a reduction reaction. So they're always either gaining or losing an electron in the process. The free electron is the only thing that can oxidize a PFAS molecule and break it down to its constituent elements. In this case, in the case of carbon in PFAS, that will be oxidized to carbon dioxide, and in the case of the fluorine in PFAS, that will be oxidized to fluorine gas or free fluorine. In the electrochemical oxidation process, a charge jumps from the anode to the cathode, and in that process, a free electron is generated on the surface of the anode. The PFAS in the water must come in contact with the anode surface in order for the carbon-fluorine bond to be broken and the PFAS to be oxidized. And while this is happening, there are a variety of other constituents in the water that are also coming into contact with the anode, and including the water itself, and they are turned into a mix of other oxidants which then go and aid in the breaking down of organics in the water, including PFAS. So this is a picture of a system that is used, multiple systems that are used to treat PFAS, electrochemical oxidation systems. This presentation will showcase bench scale and pilot scale case studies. So the left is a bench treatment system that operates in batch mode, the middle is a continuous flow pilot scale system, and then on the right would be a permanent installation, so someone's full scale, large scale system. So as I mentioned before, there are filtration and sequestration technologies that do a very good job at taking PFAS out of water streams, such as granular activated carbon, reverse osmosis, nanofiltration, ion exchange, and foam fractionation, and they are currently being used in drinking water, wastewater, and industrial waste treatment plants today. In one way or another, these will create a saturated media or a side stream that must be disposed of. So concentrating PFAS before sending it to a destruction technology has been the most economical solution thus far, and these streams are the focus of the presentation. landfill leachate specifically, and the reason why we care so much about leachate is because despite landfills not being a producer of PFAS, they unfortunately are a receiver of PFAS wastes, whether that's from household items, firefighting foams, or any of the side streams listed here. They are a huge PFAS sink, with 50% of PFAS in the environment being sourced by landfills. And all of these streams will be regulated if PFOA and PFAS are classified as hazardous compounds under CIRCLA, which we project will happen in the summer of 2024 according to the EPA's PFAS strategic roadmap. So looking at some landfill leachate, this was a customer example. I'm from Massachusetts, so oftentimes we'll look at these 6 compounds listed here in the table. We call them the Massachusetts 6, and they are currently being regulated in drinking water. So we figure that these 6 will follow suit in other states and will follow suit for future wastewater and industrial discharge regulations. So looking at percent destruction versus watt hours per gallon, going all the way up to 178 watt hours per gallon on the x-axis. What I like about this graph is that at 56 watt hours per gallon, we are already seeing above 95% destruction, and past 56 watt hours per gallon, the percent destruction stays roughly the same. So if you think about how much 53 watt hours per gallon is, you probably have a 50 watt light bulb in your home right now. If you were to stick that light bulb into 1 gallon of water and leave it there for an hour, you will have degraded, according to this example, 1,000 ppt or nanograms per liter of PFAS, over 95% for each species. So that equates to pennies per gallon in operational costs. And not only are we destroying PFAS, electrochemical oxidation is agnostic to any organic in the water, so we are destroying ammonia, in this example, at the hundreds of milligram per liter range down to non-detectable levels by about 75 watt hours per gallon. Also destroying COD and generally any organic in the water that attributes to the nice black color that is raw landfill leachate on the left of these pictures. And then on the right is treated landfill leachate. We like to say at clarity that this looks like a nice flight of beers. And then for bench treatment of foam fractionate, which is a significantly higher starting concentration of PFAS, we still have nanograms per liter here, or PPT, but this is about 5 million, so about 5 milligrams per liter or parts per million starting concentration of just these 6 compounds totaling. And we're taking that down to less than half a milligram per liter by 67.2 watt hours per gallon. And the percent destruction at 68 watt hours per gallon is above 90% for the sulfonic acids, the carboxylic acids, and all of the other PFAS species. What I like about this is as we continue to apply power, we do not see a greater percent destruction. So 67.2 is the optimal applied power. And then here just some raw and treated of the previous slide. We can go back if anyone wants to see that. We did a simulated brine as another bench test. We seeded the water with PFOA and PFAS to about 55,000 ppt, and by 250 watt hours per gallon, so about 5 light bulbs, we took it down to below the detection limit for liquid chromatography mass spectroscopy machines, which is about 2 nanograms per liter. And then you see actually at 800 watt hours per gallon, an increase in PFAS concentration, which you can also see here. We do adsorbable organic fluorine, which is basically the amount of fluorine bound to carbon, and it's a good indicator of how much PFAS we're destroying, also a much cheaper test. But we see we're actually getting an increase in PFAS if we apply too much power, which just goes to show that the optimal applied power is of low energy, 250 watt-hours per gallon. And that's a table for that. But I think I'm kind of running out of time, so go to the pilot tests. We usually do pilots for about 1 month. A lot of them are in leachate, so we were at a facility in Michigan, a consolidated waste treatment facility. We were treating 3 leachate streams. A lot of times when we do pilot tests, we will keep the flow rate constant and then vary the applied power, or we will keep the power constant and vary the flow rate. And for this client, their permit limits were 2,300 nanograms per liter of PFOA and 60 nanograms per liter of PFAS. In all of these examples, they were already below their permit limits for PFOA, so PFAS was the controlling contaminant. And at 26.2 watt-hours per gallon for the power scan, we were able to take it down to below their permit limits for PFAS. And then for the flow rate scan, we found that half a gallon per minute or 1 gallon per minute through this pilot system was optimal for reaching their permit limits. And then the client did only care about PFOA and PFAS because that's what they were regulated on, but for the lab analysis method using LCMS technology, we do also get to analyze all of these other compounds. Some are long chains, some are short chains, and with the applied power that we found was best for destroying PFOA and PFAS, we were also able to get very good to excellent removal in both long chains and short chains for some of these compounds. And then just one more, we tested 5 leachates for about a month in a landfill in Virginia. 2 of those streams are actually a thermal concentrate from a leachate and a reverse osmosis concentrate from a leachate. Now we're looking at micrograms per liter, so parts per billion concentration, and 6.3 watt-hours per gallon, which is a fraction of a light bulb. We're taking the thermal concentrate down to below, I'd say, 20 parts per billion. Not as great results for the reverse osmosis concentrate, but still, as the power increases, we're not really seeing any greater percent destruction. And then just a side note about the fouling of the electrodes. They do get dirty after here is 27 hours of continuous reverse osmosis concentrate processing. You'll see scales start to build up. There's a lot of iron in these waste streams coming from leachate, so we are turning this into rust. When you get like really salty streams, you'll get basically boiler scale or mineral scale on the electrodes, and after like a 30-minute or less acid clean of a dilute acid, maybe like 3 to 6% HCl, we're able to clean the electrodes. So pretty simple cleaning process. So in conclusion, with the right power settings, we're able to destroy PFOA and PFAS for our clients down to their permit limits in leachate, thermal concentrate, and reverse osmosis concentrate. We are destroying short chains as well as long chains, and we're doing this at a very low power, about 40 watt-hours per gallon. Again, equates to maybe pennies per gallon in operating cost. And then just another side note I think is really cool. When we compare the rate constants, and PFAS degradation is a first-order reaction, when we compare the rate constants between tests of different applied powers, we do not see a speed up of reactions. So that shows that PFAS destruction is mass transport limited, meaning it's all about how much PFAS you can get to the surface of the anode, rather than how much power you can apply to the system. So thank you guys so much. It was 2 minutes over, but if anyone in here or anyone knows of people who are receiving that $10 billion worth of remediation from the last infrastructure bill, you can tell them that to look into destruction as an option for disposal. So thank you guys so much. Any questions?
Do you use any catalysts in the process?
We use certain additives sometimes. That is still an R&D operation, so all of these examples here that you've seen do not use any catalysts. Awesome. Before this presentation, how many of you guys have heard of PFAS? Okay, awesome. Yeah, I just want to gauge because I really wasn't sure how, far back in the history of PFAS I am going, and whether or not people here are just learning about it, or they're in the process of looking for solutions, and kind of what the market is looking like right now. But thank you so much. Yeah. Yeah, we actually did when we were first developing the technology. This was actually a project out of someone's PhD project at UMass Amherst, our CEO's PhD project. And during that project, she experimented with a broad range of different catalysts, or coatings before settling on the one that we use here today. But yeah, we're always experimenting with different R&D. Awesome. So yeah, I think that is 25 minutes, and I'm going to pull up the next presentation. Thank you.